Problem 1, centroid.
This is our first problem where we are going to determine the centroid of x and y bar of the shaded area. So this is the example of this is our figure where our figure has a base of 3 meters and a height of 3 meters. And the shaded area of the parabolic spandrel has y is equals to y squared. So we have to determine first where is the centroid. So we can draw, we can simply put some rectangle here for illustration, which we're going to use to identify our centroid. Like this. This will be our centroid. So dA is equals to x dy. And now we are going to find the x bar. So our formula is x bar is equal to the integral of the area, where x, the location of x, dA, over the integral of the area, d. And we're going to substitute or put the value where x, the location of x, is equal to x over 2. This is x over 2. After that, we can input the value in our integral equation so that we can get the answer of x bar is equal to 0.58 meters. By integrating, we can get this answer, and we can assume that this will be our x bar. Our next problem is the centroid, or the location of y. Having the same parabolic spandrel, we can get the answer by using the same formula, but we only change the x into y. And by having the same process of integration, we can get the answer of y bar is equal to 1.71 meters. So we can assume that our centroid will be, the answer of x is 0.58 and 1.71 meters. So this will be our centroid in our first problem.
Two-axis theorem.
Now, this is our second problem to determine the moment of inertia of the composite area about the x-axis. So we are going to use the parallel axis theorem. This theorem is very important because this is used to find moment of the inertia of an area about any axis that passes through the centroid. So this will be our centroid, and our problem is to determine the composite area. So this is our composite figure, and we divided it into 3 figures. The first figure, the triangle, the square, and the big triangle. And by the application of the parallel axis theorem, by having this formula, the Ix is equal to Ix prime plus area times dy squared. And if you notice, this is 1 over 36. So this is the area, or this is the formula that we use in triangle in solving composite area. So 1 over 36 base times height cube, and having the area of the triangle and the Ix. Next is the square, having this 1 over 12 base times height cube. If you notice, this is square, but this formula is used for rectangle, but in the theory of in geometry, rectangle cannot be square, but square can be rectangle. That's why I'm using this formula in getting the parallel axis theorem. And the area, so base times height, or length times width, 4 times 4, and the Ix. And same as the first problem, or in the first triangle, I use 1 over 36 and over the base times height and the area and the Ix. And by the summation of all the answer of this, we can get that Ix is equal to 747.09 inches to the power of 4.
Problem 3, product of inertia.
And this is our third problem, where we're going to determine the product of inertia of the shaded area with respect to the x and y axis. So this is our parabolic spandrel with a height of 3 inches and length of 3 inches, and our shaded area will be y is equals to x cubed. And we are going to determine the dA first. So this will be our dA. If we assume we will draw a rectangle, and this will be our centroid, where x, the location of x is equals to x over 2, because it is the only shaded area is the upper portion, the lower portion is not shaded, so x over 2, and our y location is y, and y is equals to x cubed, and x is equal to y 1/3. By doing the integration, we can get this answer, and our formula is dixy equals to dix prime y prime plus dA, the location of x, location of y. So we can get the 0 because there is no centroid or the parallel axis that cut the figure, plus x dy times x over 2 times y. And by substitution or adding putting the value, and we will get the answer that dixy is equal to 1/2 x 5/3 dy. And we're going to have a further integration so that we can get the final answer, or the area of the x and y axis with this parabolic spandrel. So by integrating, this will be the process, and if you follow this process, you can do this 1/2 times 3/x 8 rather times y 8 to the power of 8/3, and the integration from 0 to 3. We cannot if we integrate 0, we can get 0 also. That's why we only use 3, so that we can get the answer faster, and the answer will be 3.51 inches to the power of 4.
Problem 4, composite area.
And we are now in our fourth problem, to determine the amount of inertia of the composite area above the x-axis. So if you notice, we have the same figure in the past problem, but I only changed the given of the base and the height. And this problem is also we also use the parallel axis theorem, but now I'm using the table method for easier process and easier to understand. And I divided the composite figure into 3 figures. The first figure, first triangle, second square, third, and the big triangle. And now we're going to find the area. So we are going to simply use the area of the triangle, and the dy, we will use the area of the triangle where 1/3, so that we can determine the length or the centroid of the triangle using this 1/3 times 3 plus, this is just example, 1/3 times 3 plus 3, or if you use our given, it will be plus 5 times 5 plus 5, so we can get the 6.67. And the ix prime, we will use the formula 1/36 base times height cube, and we can get the area of dy squared by simply multiplying area and the dy, but we will square this so that we can get the answer, and simply add these two so that we can have the ix of the first figure. And the second figure is the square, so we get the area of the square, where length times width is 25, and it also have the same process, but it will be 1/2 divide our times 5, or 5/2, so that we can simply get the 2.5. And the ix prime, it only it also used the process or the formula in the composite where 1 over 12 base times height cube. So this is the result of this formula, and simply add the answer. Or but first we identify the answer of a area of dy squared, multiply, have the same process, multiply and square the dy, add these two and get the final answer. Having the same process in the first figure, in the first segment, same process all the time because it is also a triangle. Use this, and we can use another type. Will be 1/3 times 10 or the base. So we can have, or this is just for example, but our given in here is 8. In 8 our base and the height, so 10, and add so that you can get the answer of the ix in third figure, and the summation of the ix is equal to the summation of ix prime. All of the answer in our three figures will be summed up so that we can have the ix is equal to 1447.58 inches to the fourth.
Problem 5, mass moment of inertia.
And now we are here in our last and final problem. We are going to identify the mass moment of inertia for this disc. So the question is, a thin circular disc has a mass of 20 kilograms and a radius of 2 meters. Determine the mass moment of inertia for the disc about the z-axis. But the first thing we should do is we should do the relationship. So we will find the relationship. So Izz is equal to the density of the integral of volume times r squared dv, and integrating in substitution some value equals the density is equal to the integral of 0 to r, or this will be our radius, or this will be 3, then plus times rather the small r, or the circulation, or this is the small r is this, where our radius or the small radius is going to the big radius, or this have this motion, multiply by 2 pi r. So this will be the radius times the thickness. So even if it's the disc is thin, but it still have thickness, and dr, and this is the integration. By integrating this, we can have the 1/4 r to the fourth. And next, Izz equals to the density multiplied by 2 pi thickness. So we get this because we integrate, or the constant, we transfer the constant, transfer out the constant, so that we can have this formula. Multiply by 1/4, or this, we can put this down, r to the fourth. And last, Izz is equal to the density times pi r squared times thickness multiplied by 1/2 r squared. So this density, we can multiply the density to this phi, or the volume. So by multiplying this, we can get mass. So by having this density multiplied by the volume, we will have Izz equals to 1/2 mass r squared. So by this formula, we can solve the mass of the disc. So by inserting the value, Izz equals to 1/2 m r squared. But this is our formula that we got in derivation. Putting the value 1/2 times 20, the mass, multiply to our radius squared. So the final answer will be 40. The disc has a mass of 40.